over 53. And then it's 1.5 plus 855 over 53 plus 855 over 53 plus by 6555 over 106 is equal to 5067 over 53. Okay, I will check again. So the first term 1458 over 53 is correct. And 5067 over 53. So finally, you get your y bar. Okay, so y bar is equal to 5067 divided by 1458 over 53. Okay, so 5067 divided by 1458. So it's equal to 3.475. From the top. Okay, or 2.5247 or 2. Yes. Someone has a question?
Sorry, sir. I think it's inches, not millimeters.
Ah, I think you're right. No, I think you are absolutely right. Thank you. Okay. From the bottom. Thank you. Okay. So now you see that now. Okay. So you can. Okay. So now this y bar is taken. Okay. When everything is changed to what? Aluminum. Okay. So again, the same thing. So the next thing that we want to do is calculate IZZ of 1. Okay, so like what I've done on the video before, or like what you have done on dealing with second moment of area in the shearing stress is the same thing. Okay, so over here, once your table is sorted out, everything is straightforward. So IZZ.
Eugene, I had a question.
Yes.
Why did you do 6 minus 0.5 over 2 for y bar?
Because over here, right, this is 0.5, right? And the individual centroid, right, from here to here is 0.5 divided by 2. Or from the bottom. Yeah, from the bottom, sorry. Either way, if I let me get rid of this. So it's basically the distance from here to here is 0.5 divided by 2. And then the distance from here to here is 6 minus by 0.5 divided by 2. Does that make sense?
Yeah, it does. Thanks.
Okay. So from here, right? So that's why once you the thing about this is once you have your table sorted out, okay, everything is straightforward already. Okay, so I'm not even looking at geometry now. I'm not looking at the shape. I'm just looking at my table now. So 1 with 0.5 cube divided by 12 plus by the area of 6 multiplied by 3.4753 minus by 0.25 squared. Okay, so this is equal to 1 times by 12 times by 0.5 power 3 divided by 12. So this is 0.125 plus 3.4753 minus 0.25 squared times by 6. So this is 62.415. Okay, 4154. So it's equal to 0.125 plus by 62.4154 is equal to 62.5404. Let me do it again. So 1 times 12 times 0.5 power 3 divided by 12, 0.125, 3.4753 minus by 0.25 squared times by 6, 62.4154. So 0.125 plus 62.4154 is equal to 62.5404 inches cubed. Like what I said, I'm not even looking at the geometry. Okay, so all I do is just bring this down, right? Bring this down. No thinking. The thinking is just to tabulate the data. Okay, just bring this down. You can see for yourself, right? This is the area, N area, right? Multiply by this. I hope you all adopt this, okay? Or you can, in fact, once you adopt this, once your layout is correct, right? You like what I do, I set up an Excel table, okay? And you can always check, okay? Online or at home testing, right? You can use whatever. Right, so IZZ2 is equal to IZZ3. So again, now your N changes, right? It's 95 over 53 multiplied by 0.5, 6 cubed divided by 12, plus by the area is 285 over 53. And then still 3.4753. Hey, minus by 3, and then the whole thing squared. Right. So now this will become 95 over 53 times 0.5 times by 6 power 3 divided by 12. So this is equal to 16.1321. Let me check again. 95 over 53 times by 0.5 times by 6 power 3 divided by 12. 16.1321 plus by 285 over 53 multiplied by 3.4753 minus 3 close bracket squared is equal to 1.2148. Let me do it again. 3.4753 minus 3 squared. That's by 285 over 53. 1.2148, correct. So 16.1321 plus a 1.2148 is equal to 17.3469 inches. Why do I say cube? Okay, inches to the power 4. Okay, let me do it. 16.1321 plus 1.2148. 17.3469. Okay, and then finally, IZZ 4. So again, 95 over 53 multiplied by the width multiplied by the depth divided by 12 plus by 57053 over 53 multiplied by 3.4753 minus by 5.75. Okay, so 95 over 53 times 12 times 0.5 over 53 times 12 times 0.5 power 3 divided by 12 is equal to 0.224. Yeah, let me do it again. 95 over 53 times 12 power 3 divided by 12. Go 2241 plus by 3.4753 minus 5.75 squared multiplied by 570 over 53. So it's 55.6477. Let me do it again. 570 over times by 3.4753 minus 5.75 close bracket squared. 55.7, yep. 55.6477 plus by 0.2241 is equal to 55.8718 inches to the power 4. So finally, your IZZ, okay, so it's equal to 62.5404 plus by twice, because IZZ 2 and 3 are the same, 17.3469, okay, plus by 55.8718. Okay. So this is, when I mark your quizzes and your term tests, I realize that you all make a lot of like mistake, okay, on calculating your second moment of area. In order to calculate second moment of area accurately, you can see here, okay, it's nothing to do how smart you are or what. It is how organized you become. Okay, don't do what the solution manual does. Okay, put everything in one equation, then come out. Okay, you do in stages. At least you can check where you have gone wrong. That's why I'm still adopting this technique when I'm showing you. I know it takes more time, but at least you can check. Okay, the most important thing is you can check. Okay, so that's your IZZ. So from here, we can now calculate the maximum stress acting on the aluminum. Okay, so now let's do some analysis first. Okay, let's do. So we know that this is equal to 2.5247. Sorry, from the top, right? It is equal to 3.4753. Okay. So now I'm going to sketch. Okay, I'm going to sketch this diagram again. So we are going to sketch. So if we look at the structure now, right, we're going to look at the structure now. Right, so this is how our structure look like. And then we have a second. Okay, this is how our structure look like now. So, and I'm going to draw our transformation. So this is Y and this is Z. And we know that from the top, right, we have our centroid from the top is 3 point, right? So this 3.4, so this is from the top. Okay, so we know from the top, right, we're going to have 3 point, from the top is what, 3.4753, okay, 3.4 centroid. And based on our analysis on the bending moment arrow, you can see there's our bending moment arrow over there. The top is under compression, right? So we write down here, this is under compression. This is under tensile. Okay, that's under compression. And then we have under, and then we have tensile. Okay, so from here, we want to, so the question asks, determine the maximum stresses. Okay, determine the maximum stresses. So we know that the maximum stress is always the greatest distance away from the centroid. Yes or no? So over here, this is our centroid. Right? And then we are also aware that the distance from here to here, this is equal to 2.5247. Okay, 2. So based on the distance from the centroid, we know that our maximum is going to be in the compression side. Okay, so now, so let's calculate for aluminum. Okay, aluminum. So we know at this point over here, which I'm going to draw, okay, at this point over here, right, stresses will be at the maximum, Okay, or not this point, on this line. Okay, so if we look at this entire line over here, okay, so maximum tensile will be on that line, right? So from here we calculate for aluminum, right? So we can